Thank you for the kind introduction. So this work is joint work with professors Mark Silberstein, Takahiro Shinagawa, Peter Pietzuch, and Lluís Vilanova. I'm going to be talking about optimizing the performance of virtual machines which still have some substantial pain points in certain areas. So a bit of background about virtual machines. Virtualization allows applications to run within their own virtual environments. They allow the consolidation of physical resources for efficiency. Virtual machines run in isolation of one another for security, and also they allow fine-grained physical resource provisioning for flexibility. Overall, virtual machines improve the utilization and the resource utilization and reduces hardware costs in cloud computing centers and hyperscalers, reducing the overall TCO. However, virtualization comes at a cost. Nothing is free. And in order to provide virtualization, we need additional mechanisms to provide the necessary abstractions and isolation requirements which impact the performance. In particular, the memory translation overhead in virtual machines can account for a lot of slowdowns in applications. For example, it can affect an application's performance by up to 2.4 times just because of the address translation overheads. Now let's see how memory translation works in current systems and in virtual systems. Here we can see several components of a bare metal machine. We have an application and an operating system which access memory utilizing virtual addresses. These virtual addresses are then translated to physical addresses utilizing the MMU or the memory management unit. The memory management unit translates virtual addresses to physical addresses by traversing a hierarchy of page tables that is provided by the operating system. On traditional or common x86 64 machines, this would require up to 4 memory accesses to translate a single virtual memory address to a physical memory address on a TLB miss. Translation under virtualization is not that simple. So over here we have an application and an operating system running within a VM, and we have a couple of these VMs running on top of a hypervisor on top of a physical server. Applications within the virtual machines utilize guest virtual addresses in order to access memory. Virtual machines themselves utilize a virtualized physical address space called a guest physical address space in order to access memory. Different virtual machines have different guest physical address spaces in order to ensure inter-VM isolation. Finally, memory is accessed using the host physical address, which is the true physical address of the machine to access the memory. There are currently two main approaches to virtualization. The first one is nested paging. Here we can see again an application and an operating system running within a virtual machine. The operating system exposes a page table just like before, but this page table translates, unbeknownst to the operating system of course, guest virtual addresses to guest physical addresses. The hypervisor then provides an additional hierarchy of page tables, and these page tables translate guest physical addresses to host physical addresses. In order to translate a single guest virtual address to host physical address, we need to traverse both hierarchies of page tables. Since the guest's page table entries themselves are guest physical addresses, in order to translate guest virtual addresses to host physical addresses, we will need to traverse the nested page table hierarchy each time. This can lead to up to 24 memory accesses to translate a single guest virtual address to a host physical address upon a TLB miss. Next, we have shadow paging. In shadow paging, we can see here again application and operating system, which provides a set of page tables. These page tables as well translate guest virtual addresses to guest physical addresses. However, unlike the prior approaches, the operating system's page tables are never actually in direct use by the translation hardware in order to perform the memory translation. Instead, the hypervisor provides a set of page tables called shadow page tables, which translate directly from guest virtual addresses to host physical addresses. The hardware, or the MMU, traverses only that set of page tables. In order to construct these page tables, the hypervisor needs to monitor all of the guest's operations on the guest page table. meaning that every guest page table modification operation would require the hypervisor to intervene within that operation, causing a lot of VM exits and a lot of overhead for the system. On the other hand, since the hardware only traverses the shadow page table hierarchy, this results in native address translation performance, meaning we need up to 4 memory accesses to translate guest virtual addresses to host physical addresses upon TLB miss. Both address translation and management are important in systems. So for example, if we have an application that requires a lot of memory allocation or spawns additional processes, this would require a lot of page table modification operations. If we have other applications which have vast data sets, this would cause a lot of TLB misses, which would require a lot of page walks. Current solutions optimize one at the expense of the other. Nested paging, just to sum up the previous 2 slides, can cause up to 24 memory accesses in order to translate a single guest virtual address to a host physical address. On the other hand, in this method, it is not required for the hypervisor to intervene on every guest page table modification operation. In shadow paging, we do have native address translation performance, but the hypervisor needs to intervene on every guest page table manipulation, causing VM exits and a substantial overhead to runtimes. Our goal in this work is to enable efficient translation and management within virtualized systems. Our work, called Translation Pass-Through, or TPT for short, has 3 main design goals. The first is to provide the ability of virtual machines to have self-managed direct guest VM to host memory translation. We would like to achieve this in order to enable native address translation performance. Secondly, we would like to efficiently maintain protection and isolation between virtual machines. We would like to achieve this without compromising on other system overheads, such as hypervisor interventions on guest page table modification operations. Finally, we would like to have ease of integration and maintenance of our system for fast adoption and backward compatibility. We address our first design goal by allowing the guest to directly translate guest virtual addresses to host physical addresses. In order to achieve this, the hypervisor in our system exposes a read-only map to each VM. This read-only map essentially translates guest physical addresses to host physical addresses. So each virtual machine will have such a map and will know what its guest physical address corresponds to in terms of the host physical address space. Using this map, the guest can construct its own pass-through page tables. These pass-through page tables translate directly from guest virtual addresses to host physical addresses, meaning that when the MMU performs a translation, it will only traverse this hierarchy of page tables, causing up to 4 memory accesses to translate a single guest virtual address to a host physical address, which is native performance. For our second design goal, we would like to maintain efficient protection isolation between the VMs. This is quite a challenge in such a current system. Because currently, each operating system in the pass-through design has pass-through page tables, which translate directly from guest virtual addresses to host physical addresses, the guest can manipulate its own translations in order to access any host physical address of the system. Specifically, it can try and manipulate its own page tables to access the host physical addresses of a different VM running on the same machine, thus breaking isolation. Therefore, we need a new hardware component which will enforce isolation between the virtual machines. This hardware component is going to ensure that virtual machines will only be able to access physical pages that have been allocated to it by the hypervisor and not try and access other physical pages in the system. To describe this new hardware mechanism, let's take an example system where we have 3 virtual machines running on a physical system. Each virtual machine has its own set of physical pages that have been allocated to it by the hypervisor. These physical pages are scattered throughout the physical address space of the actual machine. And again, we want to ensure that a virtual machine will only be able to access its own pages within this physical address space. So our proposal is each VM will be issued a unique tag. This tag is going to identify the virtual machine throughout its lifetime and specifically when it's performing memory accesses, so we can identify which virtual machine has performed the memory accesses. We then construct a host frame permissions tag map. Each entry in the tag map corresponds to a physical page within the system as a one-to-one mapping. Each entry's value is the assigned tag of the physical page's owner, in this case the owning VM. So over here in this example, we can see that the first page of the physical memory, A, the green one, corresponds to T2, tag number 2 of VM number 2, the green one. So what happens is that when a VM accesses the page, the MMU concurrently looks up the physical page's tag value within the tag map. And then it asserts whether the tag value that has been provided by the tag map is the same as the virtual machine's tag. If the tag value of the physical page does not correspond to the virtual machine accessing it, then this access will fail, meaning that we're going to raise an interrupt into the hypervisor, and then the hypervisor can decide what to do, whether it's killing the virtual machine or raising a different error. So the hardware proposal that we have actually is available today. This is contained within existing hardware. Architectures such as AMD's SCVS&P already incorporate such page tag mechanism. The problem is currently with today's technologies is that AMD's SCVS&P has this technology intertwined with memory encryption and also with nested paging. So we could not isolate just that one bit, but we believe that with minor microarchitectural updates, we could just isolate that mechanism and take advantage of it separately. There are other mechanisms, such as armed Sherry and RISC-V PMP, that can also help us achieve this goal. This goal, we would like also to achieve that the physical page tag checks will overlap the memory translation performance, the memory translation procedure. Please refer to our paper for more information how this overlap can be actually achieved. So back to our second design goal of maintaining protection and isolation between VMs. As we have said, the hypervisor will issue a unique tag to each virtual machine, and we also provide the tag map that will tag each physical page within the system. This design allows us to essentially decouple the translation and isolation mechanisms within the system, and it also allows us to overlap the page traversal mechanism as well as the tag checking mechanism. For our last design goal of integration and maintenance, I'll go over TPTs or translation pass-throughs high-level design. For a deeper dive into each of these components, please refer to our paper. First, TPT retains the use of nested page tables for backwards compatibility. This helps us retain the current boot procedure which virtual machines have and allow us to minimize the modifications that are required in both the guest operating system and in the hypervisor. Secondly, we enable TPT only on select application where translation performance matters. When enabled, TPT implements a dual page table design transparently. The original page tables, which are nested page tables that translate from guest virtual addresses to guest physical addresses, are already there, and the changes are seamlessly reflected to our pass-through page tables. Applications can utilize either the nested page tables or the pass-through page tables for native application performance. Also, regarding this design, the hypervisor can force applications to utilize the nested page table design when required. For example, when we're performing VM migration or when we're performing forceful page reclamation in the system. Finally, TPT provides the VM itself with the capability of constructing and maintaining its own pass-through page tables. This is achieved by first enlightening the virtual machine by exposing it the guest physical address to host physical address map for each VM. And we're also utilizing the internal Linux mechanism of PVOps in order to reflect the changes from the traditional page tables into the pass-through page tables seamlessly and with minimal overheads. We evaluate several workloads under the following configurations and compare it to TPT. First, we evaluate the workloads under native configuration, that means no virtualization, and this serves as our upper bound on performance. Next, we evaluate the applications under virtualization, first with shadow paging, and then with nested paging. For TPT, we evaluate two different models for two different microarchitectural implementations. The first one, TPT opt, is an optimized implementation in which we assume that the page table walks and the physical page tag checking can fully overlap. The second configuration of TPT naive doesn't assume that things can be overlapped and are performed sequentially. That means first we are performing the page table walks, and then we are performing the page tag checking. We evaluate the performance of two applications here. First, we evaluate KC Bench, a kernel compilation benchmark, and PageRank. The first application, KC Bench, stresses the page table management of the actual system. And PageRank has a relatively vast data set which stresses the memory address translation. What we want to show is that TPT achieves both efficient memory translation and efficient page table management. The y-axis in this graph is the application slowdown over native execution. And the x-axis are the applications, where each bar inside the graph shows a different configuration. So in this specific cluster for KC Bench, the TPT performance, TPT opt is the pink one, and TPT naive is the purple one. In KC Bench, we can clearly see a slowdown of shadow paging over native execution. This is because KC Bench spawns many compilation processes in order to compile the kernel. And when you're spawning processes, you have to duplicate and manipulate the page tables along with it, which causes a lot of overheads and VM exits. Thus, we can see the slowdown. On the other hand, TPT does not have such a slowdown as it does not require hypervisor interventions on page table modification operations. For PageRank, which has a relatively vast data set and has numerous TLB misses, we can see a high slowdown of nested paging over native execution, specifically a 2-time slowdown. This is because of the workload's access pattern, which is relatively random, causing a lot of TLB misses, which causes 2D page walks to happen. On the other hand, TPT does not exhibit noticeable overheads regarding memory address translation, because we're taking advantage of the pass-through page tables, which translate directly from guest virtual addresses to host physical addresses. We have evaluated other benchmarks, such as XS Bench, Canil, BFS, Connected Component, etc. And the geo mean of TPT does not exhibit slowdowns over native execution. We also evaluate memcached serving Facebook's ETC workload. We want to show how memory translation overheads affect the tail latencies of such applications. This is the latency throughput graph of the results, where the y-axis is a 99th percentile tail latency, and the x-axis is a throughput. We define a tail latency of 500 microseconds, and we want to achieve the highest throughput while staying under this SLA. Here we can see the performance of the different configurations. We can see that nested paging performs the worst and has a worst performance degradation of up to 1.3 times slowdown from native execution. Again, this is because we have a relatively vast data set, and memcached incurs a lot of TLB misses, which triggers 2D page walks, which affects the tail latency. On the other hand, we have TPT opt, which matches the performance of native execution. Also, shadow paging matches the performance of native execution, because in this specific workload, there are not a lot of page table modification operations. TPT naive, on the other hand, still performs better than nested paging, but is not far behind from TPT opt. To conclude this work, current virtualization technologies couple together isolation and translation. Therefore, they suffer from performance degradation and undesirable overheads. These overheads are expected to increase with the advent of deeper page table hierarchies, such as Intel's 5-level page tables. TPT eliminates such overheads by leveraging emerging technologies such as AMD's SCV-SMP. TPT accomplishes this while retaining backwards compatibility to non-TPT VMs and non-intrusive changes to both the hypervisor and to the kernel. Thank you very much, and I'll gladly accept any questions.